All right, so we'll look at how to basically prepare these. One thing to keep in mind is that think of the hemiacetal as more of an intermediate. And the acetal is essentially the product. There's only kind of a rare case with cyclization of like an intermolecular version where we stopped at the hemiacetal. That's just kind of one outlier. Just think of this typically as an intermediate. The acetal is the product. For these, your starting material is always an aldehyde or ketone. So you could have this ketone. Or an aldehyde, nothing else. So if it's a carboxylic acid derivative, you're not going to do this type of reaction. So for example, if you start with this, don't even consider the hemiacetal-acetal process. All right, so these are going to be reacting with an alcohol, and we'll do this one as just a regular alcohol, and we'll react the second one with a diol to do kind of a cyclic version. You can use pretty much any alcohol. We always do this under acidic conditions. And then let's start with just the products, and then we can talk about the mechanism if you want. But basically, what's going to happen is you first get the hemiacetal, where this O-ethyl group adds to the carbonyl carbon, and this oxygen becomes an OH. Let's get the OH. And, oops, the O-ethyl adds. All right, but again, this is your hemiacetal. Think of that as kind of an intermediate. Don't stop at this stage. All right, this will continue to react and replace the other OH with an O-ethyl group. Okay, and then this is your acetal. All right, so you can do this with an alcohol using a ketone or an aldehyde. Okay, so here's an aldehyde, and let's do this one, just predicting the product, with a diol. Okay, again, you're going to have acid. Let's use this 3-carbon diol. All right, we can kind of separate the ends, one OH and then the other. All right, so let's start. We'll add this red OH. So the oxygen with the rest of this chain will add in to the carbonyl. That oxygen will become an OH, just like we did above. So the carbonyl oxygen becomes an OH. This red oxygen then bonds. Like that. All right, now, instead of using a second molecule of alcohol, your second alcohol is already part of the molecule. So then this one will bond to the hemiacetal carbon, and you'll lose that OH. So again, think of this as your intermediate. Okay, you lost the black OH. The red oxygen is still bonded. And then this blue oxygen is now also bonded to the acetal carbon. And then they're connected by these 3 carbons. Okay, so that's just predicting the products. Does anybody want to go through the mechanism for one of these? Yeah. I don't know. Huh? Some of you also know too. If you don't know what I mean, you don't know what I mean. So let's go through the mechanism for this one. To get to the acetal, we're going to use, in this case, an aldehyde, acid, and ethanol. All right, no excuse for anybody missing the first step. So the first step is always protonating the carbonyl. Okay, from there we're going to add our alcohol as a nucleophile. And I'm just going to use regular arrows instead of equilibrium arrows to keep it simple. All right, so this will add to this carbonyl type carbon. All right, now we've been doing a little bit in class, just doing the intramolecular proton transfer, which you could do, but you do miss out on actually drawing the hemiacetal intermediate if you do that. So we're going to do this as kind of the 2-step process. And first, just use a base to take that proton off. All right, so here is our hemiacetal. All right, now we want to keep this O-ethyl group, so don't protonate that. You want to protonate the thing you're going to get rid of, which is the OH. All right, so we'll protonate that one. All right, from there, now you have water as a really good leaving group, so we do kind of an assisted leaving group departure where you use the lone pair on the neighbor oxygen. So bring that down, lose water. I'll straighten it up here. Okay, so by doing that step, you effectively have a new activated carbonyl, and that you can add the second equivalent of alcohol. And you always do these with an excess of alcohol around. Okay, so you get this. And finally, just a base. We'll take that proton off. And there's your final product, the acetal. No. No. Nothing you need to be specific on with equilibrium arrows. Really the only place where equilibrium would probably even come up might be, I'm sure you've seen several of these in the old exams, like multiple choice questions where I ask which gives the highest percentage of hydrate. And that's basically an equilibrium. Does equilibrium fall to the side of the hydrate, or does it fall to the side of the starting carbonyl compound? Oh, let me get her and I'll get you next in the back.
Can we go over alpha, beta, and saturation, please?
Just what it is or what it does?
Yeah,
both?
both.
Okay. And, yeah. Yes. So on the exam, it's totally fine. You can use B with a lone pair, which actually I kind of recommend that because if you don't, you need to use something with a lone pair, but it has to be something in this reaction mixture. So, I've seen people like use a nitrogen with a lone pair, which yes, that's a base, but you don't have that added. So if you stick with the B, you're just being generic that it can be anything with a lone pair, and that's fine. Let's look at the alpha-beta unsaturations. All right, so first thing, I just want to kind of recap how to pick out the alpha and beta carbons. So think of the carbonyl position as kind of the starting point or the zero position. It does not get a letter. And then any carbons attached to that can be lettered in Greek. So like here you could go alpha, go down the chain, beta, gamma, delta. The hydrogen, that's not a carbon, so you would not give it a letter. Okay? Now, if we do this one here, again, think of the carbonyl as your starting point. There's a carbon attached on the left. That's an alpha carbon. But there's also a carbon attached on the right. That's also an alpha carbon. You can have two alpha carbons because you can have two carbons attached. And then here you can go alpha, beta, gamma. And then in this third compound, we have alphas. On the left, you can go out to a beta before you run out of carbons. On the right, we can go alpha, beta, gamma. All right, now, on this third compound, you have the double bond between alpha and beta. This is an alpha-beta unsaturated. This is a ketone, so we call it a ketone. You can have other alpha-beta unsaturated carbonyls. So if you have a hydrogen over here, it would be alpha-beta unsaturated aldehyde. You could have an alpha-beta unsaturated ester, different things. So if you have this, so far there's really only one reaction we've talked about that takes advantage of this alpha-beta unsaturation, and that is addition of cuprates. All right, and really, doing this is pretty simple. You can have any R group attached to the copper, and what that's going to do is add to this beta carbon, and you lose that double bond. So just generically here, you end up with an R attached to the beta carbon. All right, let's do something a little more complex. All right, so this is probably a little more complex than you'll see, but it really doesn't change anything. All you're going to do is put this great big R group attached to that beta position. So redraw that molecule. Without the double bond. And then at this beta position, we're going to attach this entire group. When you're dealing with something bigger, always number it to make sure you don't lose carbon. So we have the double bond between 1 and 2. We have carbon 3, and then 4 has 5, and 4 has a methyl on it. Any questions on this? Yeah.
Could it go, would there ever be a molecule that we were given where there were 2 alpha beta unsaturations? Would we have to choose, or would it do both?
Nah, don't worry about that. Okay. Don't worry about 2 alpha beta unsaturations. Any other questions here? Yeah.
I just wanted to clarify, when you use the diball, is that only on esters, or do you use it on others?
So that's kind of some confusion on my part. So for diball, I only covered in class esters. So that's all I will give you on the exam. technically it will also reduce acid chlorides. And there's a few questions in the problem sets. I don't think I covered acid chlorides in class, so if you see dieball, it will only be with an ester. Okay? Yeah?
You do a reaction that requires like protecting and deprotecting?
Yeah. You want an alcohol or carbonyl protecting? Of course. Okay. All right, so let's start with protecting an alcohol, and the reactions you have to worry about protecting an alcohol from. So things that alcohols will do. And oxidation. So alcohols are susceptible to being oxidized, so be careful with that. Be careful with LAH because the hydride reacts with that proton on the OH. Grignard reagents, organolithium compounds. These are probably the most common reagents you'll see where if you have an alcohol, you may need to protect it. Okay, so for example, let's say you have this molecule here. You want to use phenolithium to add a phenyl group into that aldehyde. So what you want is this. Okay, but the problem is that instead that phenyl group will go and react with the acidic proton. So the way around that is just to protect this alcohol. So for alcohols, protect them with the silicon group. All right, so TMSCl on a base. I don't know, there's a bunch of different bases you could use here. I think maybe we did pyridine in class. Okay, this only affects alcohols, so you don't have to worry about the aldehyde or anything else. We put this TMS group on the oxygen, and it basically renders that oxygen pretty inert. So now, do the reaction you want. Okay, so we add our phenyl group to the aldehyde, and then the last step is to deprotect. So anytime you protect, you have to deprotect. And for the silicon group, just add fluoride. It's usually fluoride and water. Water provides the proton to go back on the oxygen. Okay, so that's the OH protecting groups. Everybody clear on that? Yeah.
This might relate to the mechanism, but like, there's like the TMS then Cl. Is that just like, is that a leaving group that just go away? Is that why?
In this step?
Yeah.
Yeah, so yeah, basically what happens, the base takes the proton from the oxygen. That negative oxygen attacks the silicon and displaces the chlorine.
Where's that fluorine come from?
The fluorine, you add that. Like, this is like a third step. Yeah. Any other questions on this one? All right, so let's look at aldehyde and ketone protection. Okay, so the things you have to be worried about with aldehydes and ketones. You have to be worried about reductions like LAH, sodium borohydride. These can get reduced. With the aldehyde, you have to worry about oxidation. So if you add chromic acid to an aldehyde, that'll give you a carboxylic acid. Grignard reagents, lithium reagents. Those probably the most common group of things there. Now with these, we protect them as the cyclic acetals. So let's say see what I want to do here. All right, let's just say you have this, and maybe I want to, again, add a Grignard reagent to this acid chloride. Because this is has the leaving group, this phenyl will add twice. And what we want is this. But the problem is that phenyl group will also want to react with that ketone. So this is where we can selectively protect an aldehyde or ketone in the presence of another functional group like this acid chloride. So for this, add an acid. I usually use this paratoluene sulfonic acid, but if you just write H+, that's fine. And this diol, you could use 2 or 3 carbons between the 2 alcohols. It doesn't matter. So this will only react with the ketone, it won't touch that acid chloride. So we've protected that ketone. Now you can add your Grignard reagent. It'll add to the acid chloride. It's not going to bother the acetal. So it'll add the 2 phenols to the acid chloride. And then to get to the desired product, all you need to do here is add acid and water, and that'll hydrolyze the acetal. It's kind of small there, but that's H plus and H2O. Any questions on this part? Yep. Yeah, let's just go ahead and add that to the list to be safe. So yeah, just remember for your list, basically oxidizing agents, reducing agents, and organometallics. Those are the ones that typically will require protection if you're trying to avoid reaction with an alcohol or aldehyde or ketone. Yeah.
The difference between a diol and an acetate is that a diol has like OHs on different carbons with 2 OH groups, and an acetate has 2 OH groups on 1 carbon.
All right, let's see. So, all right, so let's look at this. We can talk a little bit about synthesis here. So we want to start with this organobromide and make either of these 2 epoxides. And if you're trying to tackle a synthesis problem, what you kind of want to be able to think about in your mind is, well, how do I get an epoxide? Well, one of the best ways to do that is adding MCPBA to a double bond. So if you're thinking backwards, what double bond do I need to add MCPBA to get this? I need this double bond, right, as opposed to the one on top. You need the double bond on the far end. So now you got to think about how to get to these alkenes. And there's different ways to do that. Like one way, if you want to stick with kind of stuff we've done this semester, you could use, at least to get to here, you could use like sodium hydroxide and do kind of an SN2 reaction to get an alcohol. And then POCl3 would dehydrate it to get to here. But the easiest way to get to these alkenes is just simple elimination reactions. For this one, this is just eliminating to give the most substituted double bond. You'll remember from Organic 1, this is a Zaitsev elimination. All right, and I'll tell you now that it's specifically covered an Organic 1 reaction in lecture. It won't be on the exam. But when you get to the final exam, there's going to be Organic 1 stuff on there. Simple. It's not difficult stuff, but it will be stuff. So just kind of be keeping your mind prepared for that. Okay, so an easy way to do that, and you could pick different bases. I don't know what I may have used on the problem set, but any base, and just to help make sure we eliminate, I want to add heat. That'll do the elimination across this double bond to give it more substituted. If you want the double bond on the end, you're getting this less substituted double bond. So organic one, we learned about the Hoffman elimination product. For that, you need a bulky base. And the most common is a tert butoxide. So what that will do, if I draw in one of the hydrogens here, that bulky base will eliminate there. Other questions? Yep.
In a synthesis problem, how would you know to use PCC instead of H2CrO4?
In a lot of cases, you can interchange the two. So just, let me see, I can give you a couple ideas. So remember, PCC takes a primary alcohol to an aldehyde, secondary alcohol to a ketone. Chromic acid is more harsh. It'll take a primary alcohol to a carboxylic acid, a secondary alcohol to a ketone. Or an aldehyde to a carboxylic acid. So like synthesis-wise, let's say if you wanted to selectively oxidize this alcohol, if you want to do that without bothering the aldehyde, in this case your best choice is to use PCC, because PCC won't affect the aldehyde. It'll oxidize just this secondary alcohol. Now, you could, if you want to be cumbersome about it, you could protect the aldehyde, do a harsh oxidation, and deprotect it, but if you can do something in one step, that's your best bet. But if you had, let's do one other thing. let's say you wanted to do this transformation. Go from the aldehyde and add the methyl group. So the aldehyde, you can add a carbon group to that through a granular lithium reagent. So let's start with that. We want to add the CH3. Add your granular reagent followed by, you can use acid or water. Now when that adds, you get the alcohol. Like this. Okay, so to get you to the ketone, you need to oxidize. And in this case, you have, this is a secondary alcohol. In this case, you can use either of these reagents, you'll get the same thing. So sometimes you can use them both, other times you want to be more selective about which one you pick. Yep.
Are we going to have to be able to draw molecules like the tosylate and all that stuff?
No, I don't think there's any big groups you really need to remember like that. Any other questions? All right, so I'll do one other thing that somebody emailed me about. We've kind of talked about this. Hopefully most of you are pretty good on this part, but the question was just basically why, with this type of problem, the granular only adds once, whereas in this type it adds twice. And just remember, aldehyde or ketone, you can only add that group once because there's no leaving group on the carbonyl. So once you add it, you protonate the oxygen with the water. You can only add once. On the second one, though, the chlorine is a leaving group, and this also works with esters. So in this case, the phenyl will add once. Oops. But because you have this leaving group, that leaves before the reaction's over. So that'll come back down. You'll lose your leaving group. You can't stop at this ketone, so a second phenyl or whatever will add. That, and then the water just protonates the oxygen. So you get 2 additions with that. Yep.
Would it also add twice for carboxylic acid?
No. No. So actually, it might help just to briefly, and this isn't going to be 100%, but just to briefly summarize like the carbonyl groups and what they react with. So I'll do that real quick for you. All right, so with these, for your reductions, aldehydes, ketones, acid chlorides can be reduced by sodium borohydride. Then if you use the harsher reducing agent like LAH, that will reduce any of these. The diol will reduce esters and acid chlorides. As I said earlier, I would only put esters on the exam, but I'll include it in the list here. Then your Grignard and lithium reagents. So now we're outside of reductions. Those will add to aldehydes and ketones, acid chlorides, esters. Those don't react with amides or carboxylic acids. Because of the acidity of this and the lack of reactivity with the amide. And then the cuprate will just react with the acid chloride and, which isn't in the list, the alpha beta unsaturated. I should put. I think that hits most of the reagents from the synthetic transformations chapter. So kind of just keep in mind, carboxylic acids and amides, really the only thing we can react those with at this point is LAH. Yeah?
I thought you said at some point though that those aren't compatible because the H minus will just steal the other H2.
Right. So, I mean, it's more saying there's no, well, you mean why can these reduce with LAH when I said they weren't compatible? Oh, how much time do we have? So it's not compatible with alcohols or amines, but it is with the carboxylic acids and amides. The reason, to try to make it as simple as possible, it actually does pull off a proton, but the aluminum coordinates to that oxygen or nitrogen and becomes a leaving group and allows it to go away, basically. All right, so hopefully that helps. Hopefully you're well prepared for the exam tomorrow night. All right, so diol are two OHs anywhere. So that could just be that. Really, even this, this is a diol. Because they're on the same carbon, we call it a gem diol or a hydrate. And then I'm thinking, you said acetate, but I'm thinking you meant acetal?
Yes.
Okay. All right. So the acetal, there's no OHs, just two OR groups on the same carbon. Something like this. So here's the carbon with one OR group, a second OR group. And then a hemiacetal, the things are on the same carbon, but one's an OR, one's an OH. So just think of this as kind of a half acetal. So there's that carbon. Here's your OR. Here's your OH. Other questions? Yep.
On one of the problem sets, there was a synthesis question where you had to synthesize 3 different products from one starting material. Should we expect to do something that difficult on the exam?
Was that the one with starting with ethanol?
It was a benzene with an